Good morning, class! Before you left home today, think about what you used. Your smartphone, made with plastics from petroleum? The vehicle that brought you here, powered by gasoline or diesel? The laptop you're watching this on? Petroleum-based materials. But here's the fascinating question. How did that oil and gas get trapped kilometers beneath our feet? Why is it only found in certain locations? And why do some countries have abundant reserves while others have none? Over 6,000 products we use daily come from petroleum. Our modern civilization literally runs on hydrocarbons. But here's the fascinating question. How did that oil and gas get trapped kilometers beneath our feet? Why is it only found in certain locations? And why do some regions have abundant reserves while others have virtually none? Look at this map. Oil and gas are not distributed evenly across our planet. Saudi Arabia has enormous reserves, so do the United States, Russia, and Venezuela, but many other nations have little to none. This isn't random, it's the result of specific geological processes that we're going to understand today. The global economy trades over 100 million barrels of oil every single day, worth trillions of dollars annually. Energy prices affect everything from food costs to airline tickets to manufacturing. Understanding petroleum systems isn't just academic, it's about energy security, economic stability, and career opportunities for you as petroleum engineers and geoscientists. Imagine you're an exploration geologist. Your company is about to invest $10 to $50 million drilling a single well. Will you find oil, or will it be a dry hole costing millions with no return? The difference between success and failure lies in understanding one elegant system, the petroleum system. Getting this right means career success, getting it wrong means massive financial losses. Today, we're going to solve this mystery together. We'll discover why certain rocks generate hydrocarbons, why oil flows through some rocks but not others, and why petroleum gets trapped in specific geological structures. These aren't just rocks, they're the essential players in Earth's hydrocarbon story. Think about this. The oil we use today began as tiny marine organisms swimming in ancient oceans when dinosaurs walked the Earth. Over 100 million years, geological processes transformed these organisms into the energy that powers our modern world. This isn't just science, it's an epic story of transformation through deep geological time. And by the end of this session, you'll be able to tell this story yourself and apply it to real exploration problems. By understanding hydrocarbon reservoir formation, you'll be able to predict where oil and gas accumulations might exist. Evaluate whether a geological formation can be a productive reservoir. Understand why some exploration projects succeed and others fail. Make informed decisions that could save or cost your company millions of dollars. Build the foundation for your future career in the global energy industry. Let's begin our journey through one of geology's most economically important processes. Our story has 3 chapters, and like any good story, each chapter depends on what came before. Let me present the complete picture first, then we'll examine each part in detail. A petroleum system requires 5 essential elements working together. Source rock, the kitchen where hydrocarbons are cooked. Reservoir rock, the storage container with space to hold fluids. Cap rock, the impermeable lid that prevents escape. Migration pathway, the plumbing system connecting source to reservoir. Trap, the structural or stratigraphic configuration that concentrates petroleum. Plus one critical factor, timing. All these elements must come together in the right geological sequence. The trap must form before or during migration. If the trap forms too late, hydrocarbons escape to the surface. If generation happens too early before pathways develop, nothing migrates. Let's examine each chapter in detail. Now, let's follow the first chapter, rock formation. Different types of rocks form simultaneously in different environments. Let me explain how each of our critical rock types forms. Source rock formation, the kitchen. When typically 100 to 400 million years ago, though, can be younger or older. Where? Quiet marine environments, deep lakes, restricted basins. What? Organic rich sediments that will generate hydrocarbons. In oxygen poor or anoxic waters, organic matter from plankton, algae, and bacteria settles to the seafloor without decomposing. This is critical. If oxygen were present, aerobic bacteria would consume all the organic matter, leaving nothing to make oil later. These organic remains mix with fine mud and clay particles. Over millions of years, this becomes source rock typically. Marine shales, the most common and prolific source rocks. Organic rich limestones in certain marine environments. Coal and coaly shales primarily for gas generation. Key quality metrics. Total organic content, TOC, greater than 2% is good. Greater than 5% is excellent. Type of organic matter determines whether oil or gas will form. Reservoir rock formation, the storage tank. When can form at any geological time? Where? High energy environments with good circulation. What? Porous and permeable rocks that can store and transmit fluids? While source rocks form in quiet waters, reservoir rocks typically form in energetic environments, places where currents and waves sort and deposit sediments, or where biological activity creates frameworks with natural openings. Sandstones, formed from sand accumulation in rivers, beaches, deltas, and dunes. Sand grains create natural spaces between them. This is porosity. Connected pores allow fluids to flow. This is permeability. Examples: North Sea reservoirs, Gulf of Mexico sands, Permian Basin sandstones. Carbonates, limestones, and dolomites, formed from accumulation of shell fragments, coral reefs, and chemical precipitation. Initial porosity from the biological framework. Additional porosity develops through dissolution by acidic fluids, creating cavities called vugs. Fractures can dramatically increase permeability. Examples: Middle Eastern giant fields, Gawar, Bergen, Permian Basin carbonates. Two critical reservoir properties determine storage capacity and production rates. Porosity X equals the percentage of rock volume that is pore space. Determines storage capacity, how much oil or gas can the rock hold. Good reservoir, greater than 15%. Excellent reservoir, greater than 25%. Permeability, K, equals the ability of fluids to flow through connected pores. Determines production rate, how easily can fluids flow to the well, measured in millidarcies MD. Good reservoir, greater than 10 MD. Excellent reservoir, greater than 100 MD. Both properties are essential. High porosity with no permeability means oil is trapped and can't be produced economically. Cap rock formation, the seal. We also need a seal or cap rock to trap hydrocarbons. Not all rocks make good seals. What makes a good seal? Very low permeability, less than 0.01 millidarcies. Thick enough to withstand buoyancy pressure from hydrocarbons below. Laterally continuous, no gaps or fractures, common cap rocks. Shales, most common, composed of clay-sized particles. Evaporites, salt, and anhydrite are excellent seals, virtually impermeable. Tight carbonates, dense, recrystallized limestone with no porosity. As more sediments accumulate on top, our rocks are buried deeper and deeper. two processes occur. Compaction. The weight of overlying sediment squeezes grains together, reducing porosity and forcing water out. Cementation. Minerals precipitate from fluids circulating through the rock, cementing grains together. This is lithification, the transformation from loose sediment to solid rock. This process is essential for creating both the integrity of reservoir rocks and the impermeability of sealing rocks. Now let's follow our source rock as it's buried deeper into the earth. As burial continues, two critical things happen. Pressure increases, compaction occurs. Temperature increases geothermal gradient, typically 25-30 degrees Celsius per kilometer. Temperature is the key factor that transforms organic matter into hydrocarbons. Let me show you the specific temperature zones where this happens. Stage 1, diagenesis, the immature zone. 0 to 2 kilometers. Temperature less than 60 degrees Celsius. Biochemical changes. Bacteria and chemical reactions transform organic matter into kerogen. Result, no commercial hydrocarbons yet too cool to break molecular bonds. Kerogen is like a complex molecular chain, long polymers of carbon, hydrogen, oxygen, nitrogen, and sulfur. It's not yet oil or gas, it's a waxy, solid substance. Think of it as the raw ingredient that needs cooking. Stage 2, catagenesis, the oil window. 2 to 4 kilometers. Temperature 60 to 120 degrees Celsius. This is the oil window. Thermal cracking. Heat provides energy to break large kerogen molecules into smaller hydrocarbon chains. Result, crude oil generation. Heat breaks the large kerogen molecules into smaller hydrocarbon chains containing 5 to 25 carbon atoms. These are liquid at reservoir conditions. This is petroleum or crude oil. The peak oil generation maximum rate of oil formation occurs around 90 to 100 degrees Celsius. This is the sweet spot where source rocks are most productive. Think of it like cooking too cold and nothing happens, too hot and you burn your food. The oil window is our just right temperature where thermal energy is sufficient to crack molecules but not destroy them completely. Chemical transformation. I have Pfeffer Proer. Large kerogen molecules, thousands of carbon atoms, break into medium-sized chains, 5 to 25 carbons. These molecules are liquid at surface conditions, less dense than water, the crude oil we refine into gasoline, diesel, and other products. Stage 3, metagenesis, the gas window. 4 to 6 kilometers. Temperature 120 to 180 degrees Celsius. This is the gas window. Further thermal cracking too. Result, natural gas generation. Now, it's too hot for oil to remain stable. The hydrocarbon chains break down even further into very small molecules. Methane, the main component of natural gas, 1 carbon atom. Ethane C, 2H6, 2 carbons. Propane C, 3H, 3 carbons. Butane C4H10, 4 carbons. Any oil that existed here will crack into gas. This is why very deep reservoirs typically contain gas rather than oil. Stage 4, metamorphism, the dead zone. Greater than 6 kilometers. Temperature greater than 180 degrees Celsius. Result, hydrocarbons destroyed, only pure carbon remains. Graphite metamorphic carbon, too much of a good thing! Excessive heat completely destroys all hydrocarbons, breaking them down into pure carbon. This is too deep for commercial hydrocarbon exploration. We call this the dead zone or over-mature zone. Maturity summary, the complete picture. Immature zone, too cold, only kerogen exists. Early mature, beginning of oil generation, 60-90 degrees Celsius. Peak oil window, Maximum oil production 90 to 100 degrees Celsius. Optimal target. Oil plus increasing amounts of gas 100 to 120 degrees Celsius. Primarily gas generation 120 to 180 degrees Celsius. Overmature. No remaining hydrocarbons is greater than 180 degrees Celsius. Understanding source rock maturity is crucial for exploration. We can use indicators like vitrinite reflectance and biomarkers to determine maturity level from rock samples. Our hydrocarbons are now generated deep in the source rock, but they're still trapped in the tight, low permeability source rock matrix. How do they reach the porous reservoir rocks where we can produce them? This brings us to migration, the journey from source to reservoir. Migration occurs in two stages, primary and secondary. Primary migration, expulsion from source rock. This is the most difficult part of the journey, escaping the tight, low permeability source rock. Three driving forces work together. Generation pressure. As hydrocarbons form, they occupy more volume than the original kerogen, creating pressure, compaction pressure. The weight of overlying sediments continuously squeezes fluids out. Buoyancy, oil and gas are less dense than water and naturally want to rise. The hydrocarbons move through natural microfractures, bedding planes boundaries between sediment layers. Any available pathway with slightly higher permeability. Secondary migration, travel through reservoir rock. Once hydrocarbons enter a permeable reservoir rock, migration becomes much easier, sometimes thousands of times easier than primary migration. Key principle: oil and gas are immiscible with water, they don't mix, and are less dense than water. Water density, approximately 1 grams per cubic centimeter. Oil density, approximately 0.8 to 0.9 grams per cubic centimeter. Gas density, approximately 0.2 to 0.3 grams per cubic centimeter. Like air bubbles rising through water, hydrocarbons migrate upward through the water-filled pore spaces. They can travel laterally through permeable beds and vertically wherever pathways exist. They'll continue rising until they either reach the Earth's surface and escape, forming oil seeps, encounter a trap that stops their upward migration. Reservoir traps where migration stops. For a commercial oil and gas accumulation, we need a trap, a geological configuration that stops upward migration and concentrates hydrocarbons in one place. A trap must have three components: geometric configuration, either structural folds, faults, or stratigraphic rock type changes. Reservoir rock to hold the hydrocarbons. Seal or cap rock, impermeable barrier preventing escape. Without a trap, hydrocarbons simply migrate to the surface and escape. No commercial accumulation forms. Let's examine the main types of traps. Structural traps are created by deformation of rock layers, folding, faulting, or intrusion. These are typically easier to detect using seismic surveys because they show clear geometric anomalies. Let's examine each type in detail. Type 1, anticlinal trap. Think of an upside-down bowl. Formation. Tectonic compression causes rock layers to fold upward into an arch or dome shape. How it works. Hydrocarbons migrate, up-dip, up the slope along the reservoir layer. They accumulate at the crest highest point of the fold. The overlying caprock prevents further upward migration. The fold's geometry provides closure on all sides. Why they're important. Anticlines are the most common and prolific structural traps. Many of the world's giant oil fields are anticlinal structures. Famous examples: Ghawar Field, Saudi Arabia, world's largest oil field; Kirkuk Field, Iraq; Tengiz Field, Kazakhstan. Type 2, fault trap. Formation. A fracture in the Earth's crust displaces rock layers vertically or horizontally. How it works? The fault moves rocks so that permeable reservoir rock is pushed against impermeable rock across the fault surface. The fault itself, or the juxtaposition, creates a seal preventing lateral migration. Hydrocarbons accumulate on the upthrown side or against the fault barrier. Types of faults that create traps: normal faults, extensional tectonics, most common; reverse, thrust faults, compressional tectonics; strike-slip faults, lateral movement; complexity. Fault traps can be challenging because faults may also act as conduits for fluid flow. Fractures can increase permeability. Seal quality depends on the type of rocks juxtaposed across the fault. Clay smearing along the fault plane can enhance sealing. Examples: many North Sea oil fields, Viking Graben; Los Angeles Basin fields, Campos Basin offshore Brazil. Type 3, salt dome trap. Formation. Salt is less dense than surrounding rocks and behaves like a very slow-moving fluid under pressure. It flows upward, piercing through overlying rock layers like a solid glacier. How it works? The rising salt deforms surrounding sedimentary layers. Reservoir rocks are bent upward against the impermeable salt. Multiple trap positions can form around a single salt dome. Trap positions: flank traps on the sides where layers are turned up against the salt. Crest traps on top of the dome where layers drape over it. Overhang traps underneath. Salt overhangs. Why salt is special? Salt is completely impermeable, one of the best seals in nature. Salt domes can be enormous, 1 to 5 kilometers diameter, several km tall. A single salt dome can create multiple separate traps. Famous examples: Gulf of Mexico, hundreds of salt-related fields. North Sea salt structures, offshore Angola and Brazil. Stratigraphic traps are created by variations in rock type or depositional patterns rather than by structural deformation. These form during or shortly after sediment deposition or by later erosion. Challenge: stratigraphic traps are typically harder to detect than structural traps because they don't show clear geometric anomalies on seismic data. They require careful analysis of depositional environments and rock properties. However, they represent huge potential. Many stratigraphic traps remain undiscovered worldwide. Type 4, pinch-out trap. Formation: a reservoir rock layer, such as a sandstone from an ancient river channel, shoreline, or sandbar, thins laterally and eventually terminates, surrounded by impermeable rock like shale. How it works? Hydrocarbons migrate up-dip through the permeable sandstone. Migration stops where the sandstone pinches out ends. The surrounding shale provides top, side, and up-dip seals. Common depositional settings: ancient river channels cutting through floodplain muds, shoreline sands grading into offshore shales, submarine fans thinning away from their source, sandbars in deltaic or shallow marine settings. Detection challenge: these require understanding the depositional environment and predicting where sand bodies terminate. This is where petroleum geology expertise is critical. Examples: East Texas field, one of largest fields in U.S. history, a pinch-out trap. Many fields in the Williston Basin. Deltaic pinch-outs in the Niger Delta. Type 5, reef trap. Formation: ancient coral reefs, algal mounds, or other carbonate buildups that grew in shallow marine environments millions of years ago. How it works? The reef framework creates natural porosity and permeability. The porous reef limestone is surrounded by tight, impermeable basinal shales or dense carbonates. The lens-shaped geometry provides natural closure. Hydrocarbons accumulate in the porous reef interior. Why reefs make excellent reservoirs? Biological framework creates abundant pore space. Post-depositional dissolution can enhance porosity. Can have very high permeability through interconnected voids. Age of reef traps. Reefs have formed throughout geological history. We find productive reef reservoirs from Devonian 400 ma, Permian 250 ma, Jurassic 150 ma, and even Miocene 15 ma ages. Examples: Rainbow Reefs, Alberta, Canada, Devonian age. Horseshoe Atoll, West Texas, Permian. Golden Lane, Mexico, Cretaceous. Type 6, Unconformity Trap Formation. A complex geological history creates these traps through a sequence of events. Older rocks are deposited and lithified. Tectonic forces tilt or fold these rocks. Uplift and erosion cut across the tilted rocks, creating an erosion surface. Subsidence allows new sediments to be deposited on top. The unconformity surface acts as a seal. How it works. Reservoir rocks in the older sequence are truncated, cut off by the erosional surface. Impermeable younger rocks deposited above the unconformity seal the truncated edges. Hydrocarbons migrating up through the older reservoir layers are trapped beneath the unconformity. Types: angular unconformity. Older rocks tilted, creating angle with overlying rocks. Disconformity parallel layers, but with time gap erosion occurred on horizontal surface. Why they're significant. Unconformities represent major gaps in geological time and often indicate important tectonic events. They can create very large traps. Examples: East Texas Field Combination, unconformity pinch out. Many fields in the Anadarko Basin. Alberta Basin unconformity plays. Combination traps. The real world? In reality, many petroleum accumulations are combination traps involving both structural and stratigraphic elements working together. For example, a faulted anticline where both the fold and the fault contribute to trapping, a reef buildup that's also been folded or faulted, an unconformity that's also been tilted by later tectonics, a pinch out on the flank of a structural high. Real-world geology is complex. Successful exploration requires understanding how multiple geological processes interact to create effective traps. This is why we need comprehensive geological and geophysical analysis before drilling. The reservoir fluid column, fluids separate by density. Inside a trap, fluids don't mix randomly. They stratify, separate into layers by density, with the lightest fluid at the top and the heaviest at the bottom. From top to bottom. Gas cap if gas is present. Free gas phase, methane, and light hydrocarbons. Lowest density, approximately 0.2 to 0.3 grams per cubic centimeter. Not all reservoirs have a gas cap. Oil zone, liquid petroleum. Medium density, approximately 0.8 to 0.9 grams per cubic centimeter. This is the primary target for oil wells. Aquifer or water zone. Formation water, usually saline saltier than seawater. Highest density, approximately 1 to 1.1 grams per cubic centimeter. Provides pressure support for oil production. Critical contacts. Gas-oil contact. The boundary between the gas cap and oil zone. Sharp, horizontal interface at equilibrium. Depth of GOC determines size of gas cap versus oil zone. Oil-water contact. The boundary between oil zone and water zone, also called the water table of the reservoir, defines the base of producible oil. Critical for reserve calculations. Why these contacts matter for petroleum engineering. Reserve calculations. The volume of rock between GOC or top of structure and OWC contains the recoverable hydrocarbons. Well placement. Wells should be completed well above the OWC to avoid water production, but below the GOC to avoid gas breakthrough. Production strategy. Understanding fluid contacts helps optimize. Well spacing. Production rates. Pressure maintenance strategies. Enhanced recovery methods. Note, in reality, there's often a thin transition zone, few meters, between oil and water, where both fluids are present due to capillary pressure effects. But, for simplicity, we often treat contacts as sharp boundaries. Integration. The complete petroleum system working together. Now, let's see how all the pieces fit together in a complete, functioning petroleum system. Every element must be present and properly connected. The complete story. Step 1, source rock generation. Organic rich shale buried to 3 to 4 kilometers depth. Temperature reaches 90 to 100 degrees Celsius. Oil window. Kerogen thermally cracks into oil. Oil generation creates pressure. Step 2, primary migration. Pressure and buoyancy expel oil from tight source rock. Oil moves through microfractures and bedding planes. This is the escape from the kitchen. Step 3, entry into carrier reservoir. Oil enters permeable carrier bed, often the reservoir itself. Could also be a separate migration pathway connecting source to reservoir. Step 4, secondary migration. Oil migrates laterally and upward through permeable rock. Follows the easiest pathways. Driven primarily by buoyancy, oil is lighter than water. Step 5, encountering the trap. Oil migrates up dip along the reservoir layer. Reaches the structural or stratigraphic trap. Cannot migrate further due to caprock, seal, and trap geometry. Step 6, accumulation. Oil accumulates at the highest structural position. Continued migration keeps filling the trap. Eventually forms a commercial oil field with millions to billions of barrels. The timing factor, when sequence matters. Having all 5 elements isn't enough. They must come together in the right geological sequence. This is what we call the timing or temporal requirement. Critical timing relationships. What must happen for success? The trap must form before or during hydrocarbon generation and migration. The seal must remain intact from the time of accumulation to present day. Migration pathways must be available when hydrocarbons are generated. The source rock must reach maturity while connected pathways and traps exist. What causes failure? Trap forms too late. Hydrocarbons already migrated past the area and escaped. Seal fractures after accumulation. Oil leaks out over geological time. Source rock never reaches maturity. Insufficient burial. No generation. Migration pathways don't exist. Oil stays in source. Rock-tight oil. Trap breached later. Faulting or erosion destroys seal after accumulation. Real-world example? Many basins have excellent source rocks and good reservoir rocks, but no commercial fields because the timing wasn't right. Perhaps the basin was uplifted and eroded before source rocks matured, or traps formed too late. This is why petroleum systems analysis requires understanding the complete burial history and tectonic history of a basin. We need to reconstruct the 4D, 3 dimensions plus time, evolution of the geological system. Real-world example, North Sea petroleum system. Let's examine a real petroleum system to see how all these concepts work in practice. The North Sea Basin. Element 1, source rock. Jurassic Age marine shales Kimmeridge Clay Formation to 150 million years old. Deposited in restricted marine basin with low oxygen. Excellent organic content, TOC 5 to 10%. Type 2 kerogen, excellent oil source. Element 2, reservoir rock. Multiple reservoir levels, Cretaceous and Jurassic sandstones. Deposited in river deltas, shallow marine settings. Good to excellent porosity, 20-30%, and permeability, 100 to 1000 MD. Element 3, seal rock. Tertiary age shales and mudstones. Thick, laterally continuous. Very low permeability. Element 4, traps. Combination traps. Faulted anticlines. Rotated fault blocks. formed during tertiary tectonic extension 60 to 40 Ma. Element 5, migration. Source rocks reached maturity 50 to 30 million years ago. Oil migrated through sandstone layers and fault plains, accumulated in structural highs. Timing why it worked. Traps formed 60 to 40 Ma during North Sea rifting. Source rocks reached oil window 50 to 30 Ma. Traps existed before, during migration. Accumulation occurred and has been preserved to present day. One of the world's most productive petroleum provinces, with over 50 billion barrels of oil produced and billions more in remaining reserves.